Hi everyone, welcome back to our lectures. Emeku Denze is speaking. Today we'll be looking at carboxylic acids, physical and chemical properties. So we'll be looking at the physical and chemical properties of carboxylic acid in this lecture. Let's take it off from there immediately. I have a beautiful quote today from Mahatma Gandhi. Mahatma Gandhi was a crusader of peace throughout his life. He says, "The future depends on what you do today." That is a food for thought. Let us immediately delve into our learning objectives. Now, we have three major learning objectives that we'll be covering in this lecture today. Number one, we'll be illustrating the physical properties of carboxylic acids. Number two, we'll explain the effect of hydrogen bonding. The effect of hydrogen bonding, this is very important. The effect of hydrogen bonding on the physical properties of carboxylic acid. And finally, we'll write the equations for three reactions of carboxylic acid. What are they? Number one, dissociation. Two, acid-base reaction, or say neutralization. And finally, esterification reactions of carboxylic acid. So these are what we're going to be covering in this lecture. Let's immediately take it off from there. Physical properties of carboxylic acids. Now, there are about three, when we talk about physical properties, what we talk about is usually smell, boiling point and melting point, and the solubility in water. So let's look at the smell. Now, low molecular weight carboxylic acids are liquid at room temperature, and usually they have characteristically sharp or unpleasant odors. The odors are actually very sharp or unpleasant, particularly the low molecular weight ones. Now, again, carboxylic acid have high boiling and melting point. And the reason why they do have high boiling and melting point is because of the polar functional group. Remember, this functional group is very polar. What makes it? Let's see why. Now, remember, the carbonic carbon is polar, and this is also polar. So you have two functional groups. You have two polar groups in one functional group, making this highly polar. So the carboxylic functional group is very polar. So, and because it's very polar, hydrogen bonding can occur between two or more molecules of carboxylic acid from this carboxylic end. This interaction creates what we call dimer. Dimers. What is a dimer? Dimers are two identical molecules that are bonded together. That's why we call them dimer. So the formation of this intermolecular hydrogen bond is what forms this dimer. And the formation of this dimer causes carboxylic acid to have high boiling and melting point, which is greater than those of the alcohols and even those of the aldehydes and ketones. Remember, the aldehyde and ketone just have the carbonic carbon as the only functional group. But here, you have the combination of the carbonic carbon and the OH groups. So if you look at, this is what we call a dimer. This structure here is a dimer. Look at it. Now this is one carboxylic acid. This is another carboxylic acid coming to interact. So this is the dimer. A dimer here. Now remember that the polarity of carbon to this double bonded oxygen is, this is partial negative, this is partial positive. This is partial negative. Now if you come to this one again, you see between here and here, remember this will be partial positive, hydrogen partial positive, this is partial negative. So now this is partial negative, this is partial positive. Of course, this is partial negative and this is partial positive. This is what you have here. Now, this interaction here, look at this blue interaction that is on a dotted line, is the hydrogen, I will label that now, is the hydrogen bonding. This is the hydrogen bonding occurring between these two carboxylic acids, and the formation of this creates this dimer. And this dimer, this hydrogen bond is the strongest intermolecular bond, and it takes much more energy to break it down. And as a result, carboxylic acid usually have high boiling and melting point, which is greater than those of both alcohols, the aldehydes, the ketones, and of course, alkanes. Alkanes usually are very low, but let me just put it there. Let's now look at this particular table in this page. So this table illustrates the boiling point of carboxylic acid and other compounds with similar molecular weight. Remember, anytime we're going to make a comparison of physical properties, we want to make sure that those compounds have similar molecular weight. That's exactly what we're illustrating here. So in this column, I have the class, the compound, the molecular weight, and the boiling point. Let's see. This is an alkane. Alkane has, of course, 5 carbon. Now, the molecular weight is 72. And the boiling point is just 35 degrees Celsius. Or the boiling point are measured in Celsius. Now, look at eta. Remember, the eta functional group. Remember, the alkanes do not have a functional group, but the etas have this functional group. This functional group is a little bit polar, but not as polar as those of the aldehyde and alcohol. So it's actually a very weak polar bond. Now, look at eta here has a molecular weight of what? 74. And it does have the same what? Boiling point as those of what? Of the alkanes. Of the alkane here, the pentane. So here the pentane and the diethyl ether have the same functional group. Now, if you move from there a little bit down, the aldehyde, of course, in this case, we have butanol. Butanol is C4, of course. Now, butanol has the same molecular weight. Look at it. It has the same molecular weight as what? Alkane. A little bit too less than that of the diethyl ether. Now, but look at what is happening. A jump in its boiling point. The boiling point becomes 76 because of this bond is actually a polar bond. Of course, this bond, so this is partial positive, this is partial negative. This is a polar bond. That is the reason why. Now, if we go beyond that, what about the alcohol? Now, here, the alcohol we have here is 1-butanol. Of course, it's still C4. But now, the hydroxy group is in carbon number 1. Now, the molecular weight is still the same thing with those of the ether, diethyl ether, and a little bit what? 2 units greater than those of the pentane. But look at what is happening. Just look at the jump. The molecular weight, the boiling point is 118 because of the hydroxyl group functional. Remember, this is partial negative, this is partial positive. This is a very highly polar bond. Now, if you go a little bit down again, look at the carboxylic acid, which is our subject matter in this discussion. The carboxylic acid, example here is the propionic acid. The molecular weight is also similar. All the molecular weight are comparable. Look at what is happening. Just because the carboxylic acid, of course, has this. They have the carbonic carbon plus the OH group combined together as their functional group. Now, these two guys are very polar. Look at what happens here. Similar molecular weight, but look at that jump in boiling point, 141 degrees Celsius. So, when you are comparing carboxylic acid with other compounds with similar molecular weight, particularly other group of organic compounds that we've done so far, you find out that they do have the highest boiling and melting point because of the polarity of this carboxyl group and its ability to form intermolecular hydrogen bond between themselves. Yes, having stated that, we now go to the next point, still on the physical properties. Now let's focus on its solubility in water. Now, of course, what do you know about solubility? Water is the universal solvent, of course, very polar solvent. So because carboxylic acid are very polar, it behoves that they will have some level of solubility. However, what determines their solubility will be the length of the hydrocarbon chain. So the carboxylic groups can hydrogen bond with water. That is true. It can easily hydrogen bond with water. Now, of course, what is the determinant? The length of the hydrocarbon or the hydrophobic group. So if the length of the hydrocarbon or the hydrophobic group or the carbon chain is not too large, carboxylic acid are water soluble. So what it means is that the short chain carboxylic acid are very water soluble. And I have them here. From C1 to C4. So from metanoic acid to about butanoic acid, very water soluble. Because the carbon chain is short, it's about 4. Now, by the time you get to pentanoic acid and hexanoic acid, C5 and C6 respectively, it begins to be a little bit slightly water soluble. And then by the time you go beyond that, from 7, which is heptanoic acid and above, you find out that they become very, very insoluble because the length of the higher the length of the hydrocarbon chain, which is a hydrophobic chain, the lesser the solubility of carboxylic acid. Like I said, This insolubility is because, at this level, is because of what? The hydrocarbon chain, which is a strongly hydrophobic chain. It does not want to form water. So those hydrophobic chain is just only carbon to hydrogen and to carbon. And this chain is highly hydrophobic. So in looking at that, this to the right here is the interaction of water, the hydrogen bonding between water and carboxylic acid. So this is carboxylic acid, this is water. It can easily form this intermolecular hydrogen bond between water molecule and so the hydrogen bond it forms from, now remember this is partial positive, this is partial negative. So it is forming from the carbonyl end of the oxygen to hydrogen here. This is partial positive, this is partial, oh no, that didn't come out well. So this is partial positive, this is partial negative, this is partial positive. Again, this is partial positive, partial positive, partial negative, partial positive, partial negative. So what is happening? You find out that the partial negative, the partial positive side is interacting with the partial negative side of oxygen. I say it again. The partial positive side, which is the hydrogen, is interacting with that of the oxygen, which is the negative. And here forming this intermolecular hydrogen bond. So the ability for it to form this intermolecular hydrogen bond is what makes those low molecular weight carboxylic acid to be soluble in water. So this is the hydrogen bond. I'm going to say HB. This is the hydrogen bond. This is also another hydrogen bond here formed between water molecule and carboxylic acid. And having said that, we'll now be going into reflection questions. In this first reflection question, it says, arrange the following in order of increasing boiling point and solubility in water, respectively, from 1 to 4 by using 4 to be the highest unit. The one that has the highest boiling point of solubility will be 4. And the one that has the lowest boiling point of solubility will be 1. So that's what we're told to do. Now remember, the first thing you want to do when you see this type of question is to make sure you, at your scratch paper, calculate what? You calculate their molecular weight. I have already done that. If you calculate, this is ethanoic acid. If you calculate the molecular weight of ethanol, this is actually ethanoic acid. 2 carbons. This is carboxylic acid. So if you calculate the molecular weight, it will give you about 60.05 grams per mole. That's exactly what it's going to give. If you look at this, this is 1, 2, 3. So this is 1 propanol actually. And 1 propanol is an alcohol. And 1 propanol has a molecular weight of about 60.10 grams per mole. Again, this is an alcohol, remember? This is carboxylic acid, this is an alcohol. When you look at this functional group is an aldehyde. Remember, this is carboxylic acid, this is alcohol, this is an aldehyde. So this aldehyde is 1, 2, 3. So this is propanol. So propanol has a molecular weight of about, they're all comparable, 58.08 grams per mole. And finally, when you look at this 1, 2, 3, 4, this does not have a functional group. This is just butane. This is just butane. Butane is an alkane. And of course, remember, alkanes do not have any functional group. They are very hydrophobic. So the molecular weight again is about 58.12 grams per mole. So the molecular weights are all comparable. The difference is not much. So we can now begin to compare them, use the polar group or the functional group they have to compare how that affects their functional, their boiling point and solubility, which are all physical properties. Let's see. Now, so which one is going to be the highest? Let's start. Remember, this thing has a combination of 2 very polar functional groups, the OH group and carbonyl carbon. Remember, we just studied in the previous page that carboxylic acid, when they have similar molecular weight, will always have highest boiling point. So this is going to be the highest. I'm going to say 4. 4 will be the highest. Followed by what? Now, when you compare these two, this is a polar bond. But this is what? Also a polar bond. OH group is a polar bond. But because this one can easily hydrogen bond with itself, this is going to be what? Propanol is going to have a higher boiling point than propanol. So the OH group is much more polar than the carbonyl carbon group, the CO group. So this is going to be the 3. That didn't come out well. This is going to be the 3. And then followed by aldehyde. If you compare this, and this doesn't have any functional group, so at the end of the day, it's going to be the lowest, it's going to be the 1, and this is now going to be the one that is following it. So you find that arranging this thing is their level of polarity. So here, this is the most polar, followed by this, and this is the least polar. Or you can just say non-polar. Here, butane is very non-polar. The same thing goes for the solubility. Remember, the more polar a compound is, the more soluble it will be in water. So what do we see? What are we seeing here? This is the most polar, carboxylic acid or ethanoic acid, therefore it's going to be the most soluble, followed by the hydroxy group of the 1-propanol. The alcohols we follow. And then, again, this is going to be the least, which is 1, because it doesn't have any functional group. It's very non-polar. It's going to be least soluble in water, followed, and then this is going to be the second to the last. So you look at it, the trend in their solubility is exactly the same thing with the trend in their boiling and melting point. That is how you do this kind of. And I will ask you to expect this kind of question in quizzes and tests. We now go to the next reflection question. This one now. Remember, one of the objectives is to demonstrate. We're going to be demonstrating that now. We're going to try to draw. Now the question says, draw propanoic acid intermolecular interaction with at least 2 molecules of water and name the interaction. So what we're doing here is we're trying to demonstrate that physical property by using hydrogen bonding. That's exactly what we're going to be doing. So first of all, I'm going to draw propanoic acid. Propanoic acid has prop, means 3 carbons. So I'm going to start from here to draw it. It's going to be 1, 2, 3. And of course, I'm going to put the functional group. Let me make it a little bit bent so that so I'm going to put a functional group here, and then I'm going to put my carbons. I'm going to saturate it with the carbons. Now this is my propanoic acid. Now I said, so draw the interaction with water. The interaction is going to have with water, of course, is hydrogen bonded. So that's what I'm going to show. So I'm going to draw at least 2 molecules. That's what the question said. Now a hydrogen bond can form between this oxygen to a hydrogen, to the first hydrogen here. I'm going to put it this way. Another one can form from here. This is hydrogen, so it's going to go to the oxygen to be this. And of course, this one can also go to another hydrogen. So this, okay, I'm going to use a different color. This, let me use blue. So this is a hydrogen bond. This is a hydrogen bond. And again, this is a hydrogen bond. Hydrogen bond. Yeah, so this is a hydrogen bond. So that is, and what is the name of this interaction? Say name the interaction. The name of this interaction is hydrogen bonding. That is the interaction between propanoic acid and water. And now listen. Now, there could be an interaction again from here. Just know that there could be an interaction from here. Just know that there could be an interaction here, but it's going to form a dipole-dipole. But I don't want to go there. But these 3 interactions I formed here are hydrogen bonding interaction. And if I want to label and put my partial positive and negative, remember this is more positive. This is going to be positive. It's going to be negative. This is going to be negative. This is going to be positive. And then if this is going to be negative, this is going to be positive. This is, of course, will be negative. This is positive. Of course, this is the hydrogen will be the positive. This will be negative. So this is how. So you find that in each case, a negative is interacting with the positive, a positive interacting with the negative, a negative is interacting with the positive. So this interaction is hydrogen. And this is the reason why carboxylic acid, in this case, example, propanoic acid, is soluble in water. We now go to the next thing. We now go to the reactions of carboxylic acid. So reactions of carboxylic acid. Now there are 3 reactions we'll be looking at. I told you already, the dissociation, the acid-base reaction, and then the esterification reaction. Let's start with dissociation. Dissociation is very simple. Dissociation means carboxylic acid behaves as weak acid, of course. They are weak acids. They are very weak acid. What it means is that every acid has the ability to release a proton or a hydrogen ion in solution. What it means is that they are reluctant in giving off their hydrogen ion. every acid will give off H plus. So they are reluctant in giving. So what it means is they only give a few amount of hydrogen ion in solution. And when they do give off this hydrogen ion, of course, what happens to them? They form the carboxylate ion. And in fact, this is the form in which remember, there's a lot of this acid we find in the body. It is this form that they exist in the body fluid, particularly in the body's pH. The body's pH is basic about 7.4. So most carboxylic acid related compound exist as carboxylate ion in solution, in a basic solution. So let's see what happens here. Let's see what is happening with this. Now, in dissociation reaction, what is happening? This is carboxylic acid, of course, the COOH. This is the functional group we're interested in. What happens is that because it is acting as an acid, it loses this hydrogen ion and donates it to water. The water in this case is acting as a base, of course, a conjugate base. Is a base in this case. The conjugate base will be this one. So this is acting as a base, a proper base. Now, when it accepts it, it now becomes the hydronium ion. This is the hydronium ion. Whereas when it loses this, it develops this negative charge to form the carboxylate. So this is what we call the carboxylate ion. Remember, the negative charge here is what we call the formal charge of oxygen. And remember, we talked about formal charges in the review part of this class. So the formula is when you subtract the number of bond and dot from the valence shell. That's how you know this negative. But just know that the moment carboxylic acid loses this hydrogen, the oxygen develops a negative charge. And this is what we call the carboxylic acid. And this happens in a basic condition. So when you have the high pH, it favors the reaction to the right. And this is actually what happens in the body fluid when the pH of blood and body fluid is close to what? Basic, which is 7.4. In a low pH, what happens? The reverse of the reaction takes. So in a low pH, what happens? In a low pH, what actually happens is that carboxylate ion is acting now in this case, is acting as a base. This is a conjugate base now. And this will now be acting as the acid. What is happening here is that in the opposite reaction, this guy will now be donating this back to this to form carboxylic acid. So the direction of the equilibrium depends on the pH of the solution. This is what we call the dissociation reaction of carboxylic acid. Let's practice that with this reflection. It says complete the reaction for the dissociation of the following carboxylic acid. Remember, now I put this thing here just to let you know the emphasis. This is not this is just an alcoholic group. This cannot ionize. It cannot go into solution. This does not ionize. In fact, let me write it there. Does not ionize. It cannot react. So it has to be from this functional group, carboxylic acid. So what's going to happen? Look at what happens here. This OH will now go and get this carboxylic acid will lose its hydrogen to water so that the water will form hydronium ion and itself will form carboxylate ion. So what is going to happen? Let's see. So I'm going to redraw this. My functional group is this. Remember, it has lost this and now develops a negative charge here. And then I'm going to complete the rest of the structure. You're going to have this. Nothing happens here because this is just alcohol. Alcohols do not ionize. And then plus, remember, when this accepts this hydrogen now, it becomes hydronium ion H3O and develop a positive charge. And again, this positive charge is because hydrogen now has an excess, or oxygen now has what? A deficiency of one electron. That's actually how. So if you draw, if I'm supposed to draw the hydronium ion, look at what you're going to have. So here, if you subtract hydrogen, oxygen has 1, 2, 3, 4, 5 electrons. So if you say it's in group C, 6 minus 5, so it gives you +1. So that is how this comes about. But that is not actually what we're going to be doing in this case. So this is how you complete this reaction. For the second one, of course, this is the A part, the B part. The second one here, the same thing. I don't have any functional group to confuse you here, or to make you think a little bit. It's the brain teaser. This is straight direct. So this one is going to go and join this. So what are you going to do? I'm going to redraw this ring. And then I'm going to put this. And of course, this will become a negative plus. my hydronium ion. This is how you do these reflection questions. We go to the next one. Oh, okay, that was too fast. That was actually too fast. Okay, the next one. It says, redraw the molecule below in the form in which they exist in the physiological pH. Remember, the physiological pH is 7.4. That is the physiological pH. The physiological pH is 7.4, in which I told you, in the body, carboxylic acid exists as carboxylate ions in a dissociated form where they have lost their what? Where they have lost their hydrogen ion. Now, what I want to tell you in doing this problem, no need to put the water molecule showing me that. Just redraw it for me. I don't need you to even show me the water. Just redraw it how do they exist. Remember again, this is not going to ionize. The only ionization will be at this point. So if this loses this, if I redraw this again, this will lose this, and then I'm going to have the OH, and nothing is happening here, and this is going to be, this is what you get. Just exactly what you get in the last reflection question. The same thing happens here. Again, this is going to be lost, and when that is lost, you're going to draw this ring again. You're going to put this carbon, and then this is going to become O minus. Remember, anytime they lose this hydrogen, the oxygen develops a negative charge. So this is how you complete this reflection question. Now remember, as you're watching this video, is a lecture, is an asynchronous lecture. Feel free to do what? To pause the video, try the problems yourself, and come back and see if you got the answer and how I did it at the end of the day. So that's what you do. Okay, let's go to the next reaction, the acid-base reaction. Acid-base reaction is also called neutralization reaction. Remember, acid, again, like I said when I talked about dissociation, acid is known by its ability to donate the proton or donate the hydrogen ion. So, and in doing that, they can easily donate it to a base, and a base is that substance that has the ability to accept that proton from an acid. So carboxylic acid reacts readily with bases to form carboxylic acid salt. Of course, in any acid-base reaction, you are going to form salt and water. Every acid-base reaction is going to result to a salt plus water, whether it's an organic acid in this case, or mineral acid or inorganic acid. So carboxylic acid, of course, formed at the end of the day are soluble, because these carboxylic acid that are formed are ionic compounds. They are soluble because they are ionic compounds. Ionic compounds are usually very soluble, and of course, they usually have high boiling and melting point. So let's see what is happening again. This is a carboxylic acid with potassium hydroxide. Here is a base. So what is happening? It's going to lose this proton to this. So this proton will come and join this OH group to form water molecule. Remember, I told you it must form salt and water. And then this potassium ion will now go and join this one. Remember, the moment this hydrogen goes off, it develops a negative charge. And remember, potassium hydroxide, when in solution, will become K plus plus OH minus. Remember, OH minus. I put a plus. Now, this potassium plus is what goes to join this to form this potassium carboxylate salt. So this salt is potassium carboxylate. And we're going to talk about a little bit of the nomenclature, but not a lot of emphasis, but we're going to talk about. So this is the potassium carboxylate salt. So this is a salt. This is a salt. And this salt, like I said, is an ionic compound, and it's very soluble in water. This is an ionic compound. Ionic compound. And like I said, it's soluble in water. So this is what we call the acid-base reaction. The acid-base reaction. Let's take some reflection questions to put home this particular reaction. Let's try to understand it. Now, feel free to pause this video, try out these problems yourself, and come back to check for comprehension. Okay, let's look at this. So like I told you, what is going to happen here is that this propanoic acid reacting with sodium hydroxide is a base, the strong base actually. This guy is going to come and join these two to form water. Whereas this sodium ion will come and join this hydrogen here to form the salt. So what I'm going to have, I'm going to redraw. I'm going to have this guy here. Nothing changes here. This C will be here. Nothing changes. Nothing changes here. Now here is going to be minus. Now, if you bring this sodium ion, it's you're gonna put it just by the side to be. So I didn't like the way that came out. So this is gonna be. No, I'm gonna write here. This is gonna be sodium plus. So plus, of course, it must be salt. Remember, this is a salt and water. Now, this salt is a carboxylic acid salt, and this salt is called sodium propanoate. Sodium, because this is propanoic acid, so you're going to say propanoate. How do I come about that? Look at how we do. In naming the carboxylic acid salt, you're going to be dropping the IC and replace it with ATE. That's exactly what I did. So it becomes sodium propanoate. And this sodium propanoate is a carboxylic acid salt and is soluble in water. That's exactly how you do this problem. Again, with this one, of course, this is benzoic acid. This is benzoic acid. Reacting with potassium, this is the base. Again, that's what's going to happen. This one is going to come and join this one. This one will come and join these two. And if that happens, what do you have? I redraw this. I'm going to use the shortcut. In using the shortcut, you just put this. And then, of course, nothing happens at this point. But at this point, it's going to be a negative. And then potassium is going to be K plus. Plus, of course, water molecule. Now, this is called, again, like I said, like we did in this one, this is potassium benzoate. This is potassium benzoate. That is how we call this. So, and of course, water. Remember, it's going to form the carboxylic acid. And again, potassium benzoate is very soluble in water. That is how we do these problems. Now, in reflection 6 here, this has to do with the physical properties. Let's just take a look at it. It says, which of the following will be the least soluble in water? Remember what we said? We said the solubility of carboxylic acid depends on the length of the hydrocarbon chain. So which one is the longest chain? Butanoic acid, of course, is what? C4. This is C4. Now, pentanoic acid is C5. Hexanoic acid is 6. This is C7. So the one with the longest chain is going to be the least. Look at the question. The least soluble in water. So what is the reason? I would have said give the reason. So if I say give the reason, remember this is one of our objectives, just to look at this. So what is the reason? The reason is because heptanoic acid is the least soluble in water because it has the longest hydrocarbon chain. And because that hydrocarbon chain is a hydrophobic chain. So it's going to prevent it from being very soluble in water. So what you can just conclude, a simple conclusion, is that the longer the hydrocarbon or the hydrophobic chain, the lesser the solubility of carboxylic acid. I rephrase again. The longer or the larger the hydrocarbon or hydrophobic chain, the lesser the solubility of carboxylic acid in water. That is just an important takeaway from this reflection question. We now go and look briefly at carboxylic acid, like I said again. How do we name them? I've already chipped this a little bit from the previous two reactions I talked about. I says, so naming, how do you name this guy? The first thing you do is to name the metal, like I did. Remember when I did here? I named the metals first. Potassium benzoate, sodium propanoate. That's what you do first. You name the metal first, and then change the IC that stopped the acid name into ATE. And you don't have to put the acid again at the last. So in this case, this is 1, 2, 3. This is derived from propanoic acid. So it's going to be propanoate. So if you want to name it, you put the metal first, sodium propanoate. That is how we name them. Now, carboxylic acid, what are their physical properties? They are solid at room temperature. They are soluble in water because they are what? Ionic compounds. And of course, they have high boiling and melting point as well. They have high boiling and melting point. Again, because they're ionic compound. Ionic bonds are much more stronger than covalent bond. Again, long chain. Now, another important takeaway we're going to be talking about here is that in industry, and particularly in making drugs, long chain carboxylic acid can easily be made soluble or solubilized by converting them into carboxylic acid. So how do you do this? You do this by what? Reacting them with strong bases. Because if you react a carboxylic acid with a base, it forms a carboxylic acid salt. And if you form a carboxylic acid salts are soluble. That's exactly. So in this case, this is stearic acid. Stearic acid is a fatty acid. Stearic acid is a fatty acid. It is very insoluble because the length of the chain is 18. It is a C18 fatty acid. It's very insoluble, too long. Now, if you react it with this, what happens? Remember, this is going to go and join this. This will now come and join these two to form water molecule. Now, it's going to form potassium stearate. A potassium stearate is a carboxylic acid salt. And this potassium stearate is very soluble in water. So, this is very, very important because most of the carboxylic acid drugs are made carboxylic acid salt by reacting them with strong base so that they can easily be soluble. And that is usually the form in which they are usually given or sold as drugs. Now, so this is a question that actually reflects that. It says the structure below is a hypothetical drug that is soluble in water. So complete the reaction for its solubilization. So this is a drug. This drug is insoluble in water. Now I want to make it soluble, and it's a carboxylic acid. Remember, it's a carboxylic acid because of this functional group. Now, how do I make it soluble? It's gonna be made soluble by reacting it with this strong base again. So this strong base now, this is the base. So remember which area is going to react. Remember, like what I told you again, this is not going to react. This cannot react. Cannot react. So the only place that will react is the carboxylic acid functional group. So what's going to happen? Again, if this reacts with this, remember again, this will come and join this guy, whereas this will come and join this one here to form this. So I'm going to redraw this. So if I redraw this, let me start from this side. I have this, and oh no, okay, let me make it a little bit low. Okay, I have this, I have this. Now nothing is happening here. Remember, I'm going to put this. Then I have this conjugated benzene ring. This conjugated benzene ring here. And then I have this cyclohexane connected to it. Now, then look at where the reaction is taking place. Of course, this is going to be minus, joined by sodium ion, plus water. Now, this particular drug was insoluble at this point. In this place, it forms the carboxylate as the carboxylate salt form. This carboxylate salt is now very soluble. So this is the soluble. Let me use a different color. This is the soluble carboxylate form. Or you say let me just say carboxylic salt, carboxylic acid salt form. This is the carboxylic acid salt form of this drug, and this is very soluble. And in fact, this is usually the form in which most of these drugs are sold. And so that when you take it into your body immediately, it's going to easily dissolve and be soluble in the aqueous medium of the blood. So, having said that, we're going to now be going to the last reaction of carboxylic acid, which is esterification. Esterification simply means formation of carboxylic acid ester formation. So carboxylic esters are formed when carboxylic acid are heated with alcohols or phenols. So the combination of carboxylic acid with alcohols or phenols in the presence of an acid catalyst forms esters. They form carboxylic acid ester. So the ester linkage is the carbon to oxygen single bond of the ester group. Let's see what is happening. Look at the reaction. This is a general reaction. In this general reaction, this is a carboxylic acid. This is an alcohol. Remember, in this case, it is the OH group that is the reaction. So the arrow group can be a long chain, an open chain, or an aromatic, which is a phenol. So it doesn't matter. We're interested in this. So what is happening? What's going to happen here is that now this arrow group will come and connect to this oxygen. Whereas this hydrogen will come and join this OH to form water molecule. At the end of the day, what happens? The product becomes a carboxylic acid ester. A carboxylic acid ester will now be the carbonic carbon here has a connection to another oxygen. This is what we call the ester linkage. The ester linkage. So this C, carbonic carbon to oxygen. So the carbonic carbon to oxygen bond is what we call the ester linkage or the ester bond. Remember, We talked about this when we did the functional group. This is the ester functional group. So the reaction of carboxylic acid with alcohols or phenols will result to carboxylic acid esters and water. So let us do some practice in the reflection question ahead. In reflection question 8, it says, complete the following esterification reaction. Now, again, remember what I told you. In this reaction, in this esterification reaction, remember what's going to happen? Like I said, I demonstrated. Now, this hydrogen here will go and join this water molecule. Whereas the whole of this here will now come and connect to this oxygen. Okay, let me use a different color. Will come and connect to this oxygen here. So if you do that, what are we going to have? Let's see what we're going to have. So I'm going to start with what I have, this part. Then this O will remain there. It doesn't go away. And then it will be connected to this cyclopentane ring. Then, so this is that ester functional group. Remember, it's going to have plus water molecule. So this is that ester functional group. That is how you complete this reaction. So you can easily pause this video, try out the second one yourself, and come back and check it for comprehension. So let me quickly do this. Now, the same thing happens here again. To complete this, again, like I said, I'm going to draw this again. This one is going to be, and then this one, nothing will happen to it. So I'm going to put this. This O will remain there because this one was going to go to join this one to form water molecule. But this part will all go and join this one. So this part now will go and do what? And join this part. Oh, it's bent a little bit. I don't like the way it's bent, but it's correct. But I want it. Okay, so this is now the ester. Again, this is the ester functional group. That carbonic carbon to oxygen functional group. So, of course, remember, we're going to be forming the water molecule. So this is exactly how you do this problem. Now, in the last page, to summarize, there are 3 reactions of carboxylic acid that we've covered, and that is shown in this reaction map. Let me take one of them. In the first reaction, carboxylic acid will react with water to form carboxylate ion. That reaction is called dissociation reaction. It's going to form carboxylate ion. Yes. So if you add water to it, it forms carboxylate ion. That reaction is called dissociation reaction. If carboxylic acid reacts with a base, this is a neutralization reaction. It's going to form carboxylate. So remember, this is acid-base reaction, or you say neutralization reaction. And then if carboxylic acid reacts with an alcohol, it forms ester. Remember, this reaction is called esterification. It's said to be an esterification reaction. So this is the reaction map. And I usually encourage students to have this esterification, to have this not esterification reaction, to have this reaction map close to your heart all the time. If you can always have this reaction map close to you, you're going to always try to make a connection and remember the types of reactions of each of these classes of organic compound. And having said that, we've come to the end of this lecture. Thank you for listening. Bye.